Hi guys, and welcome to these rough and ready revision videos, which I promised you. There's a video that's already in the playlist, which is about converting binary to decimal. So we're going to start off with looking at how to convert decimal to binary. Okay, so the first thing that we always do when we have binary involved is to write down our magic number list. So we start off on the left hand side then. So 128, 64, 32, 16, 8, 4, 2, 1. Let's imagine that we have the number 5 that we need to convert into binary. So let's start off with 5. So this one should be quite simple, okay, because it's a relatively small number to have to deal with. So what we're essentially doing with this technique of converting decimal to binary, what we're looking for is the ability to make up the number 5, which we've been given, out of the numbers on our magic number line. And amazingly enough, we can always do this. Okay, so how can we make 5 out of these numbers? Well, clearly, we're not going to make 5 out of anything bigger than 4, okay, because we're not going to be able to construct 5 out of 8. So we're looking at the numbers 4, 2, and 1. And you can see straight away, because it's quite a small number and it's relatively simple, that we can make 5 simply out of 4 and 1. So 4 plus 1. Okay, so for the numbers that we are going to use to construct our decimal, 4 and 1, we simply put a 1 underneath the numbers that we're using. Okay, so we're using number 4 and 1, so we put a 1 underneath, and all of the rest of the numbers that we don't use, we put a 0 underneath. Okay, so this is our working out. We would, of course, need to put our final answer in. Okay, so don't forget, guys, always put down the final answer. This is your working out. So you would say the final answer is 5. Okay, in denary or base 10 is the equivalent of 0, 0, 0, 0, 1, 2, 3, 4, 5. Okay, 6, 7, 8. So 0, 0, 0, 0, 1, 0, 1 in base 2. Okay, and you can check these numbers if you go onto the internet and find a binary to decimal converter and vice versa. You can actually check that you've got your numbers correct if you're practicing these guys. Okay, so 5 to the base 10 is the equivalent of 0, 0, 0, 0, 0, 1, 0, 1. Okay, let's look at an example which is a little bit more challenging. Okay, and how we might make sure that we can find the numbers that we're looking for from our number line. So let's just rub this one out. Okay, and the one that we're going to look at, let's do 108. Okay, so it's a little bit more challenging, 108. Okay, it's 108 in base 10, same principle then. How do we find or make up 108 from the numbers on our number line? Well, clearly, we're not going to be looking at 128 because that's larger than 108. So we need to make up 108 out of adding together some of these numbers. So the question then is, how are we going to go about doing that? Because it's not obvious from 108 how we're going to make these numbers up. Okay, well, we go to the biggest number first, which is 64. 64 goes into 108. So that's fine. 64 goes into 108 once. Okay, and then we need to say, okay, so what's the remainder between 64 and 108? Okay, well, that gives us, it's 1, and it gives us remainder 44. Okay, so where you put these remainder numbers, guys, in your working doesn't really matter. You can do it underneath or on top. Okay, as long as you make a note of them, that's fine. So we've got 44 left over. So we do the same thing again. This becomes the number that we're going to look at. We want to say, okay, we want to make 44 out of our magic numbers again. Well, clearly we don't need 64 because that's too large. So it's got to be out of 32 and some other numbers. Okay, so clearly we're going to want 32. Okay, and then we say, what's the remainder between 32 and 44? Okay, so 44 minus 32 is 12. So that's going to be the next number that we need to look at. Okay, well, we're not going to be able to make 12 out of 16, so we put a 0 in there because it's not needed. But we are sorry, we are going to be able to make 12 out of 8 and something else. Okay, so 12 divided by 8 goes once. Okay, and then the remainder that we've got left over, of course, is 4. So the next number we need to look at is 4. Okay, can I make 4 out of these numbers? Yeah, we've got 4 here. So it's basically once there, and then we've got nothing left over because it's exact. Okay, 4 into 4 goes once, remainder 0. Okay, so our final answer, if we just fill out the numbers that we haven't used with the 0, which we did before, we can say our final answer is 108. Okay, to the base 10 is the equivalent of 0, 1, 1, 0, 1, 1, 0, 0 to the base 2. Okay, or binary. So what I would suggest you do, guys, now you've seen the basic principle, okay, you can either see which of these numbers on the magic line you can make your decimal number out of. Okay, sometimes if the numbers are small enough, it's quite obvious how you need to construct your decimal out of a variety of your magic numbers, but sometimes it's a little bit harder, in which case you might want to just keep on making a note of the remainder, okay, and then use the remainder, okay, to keep working out what your binary number equivalent is. So in this part of the video, guys, we're going to be looking at right and left shifts, and this uses a characteristic or a pattern within the binary representation of decimal numbers. So to give you an example, if we look at the number 6 in decimal, I'm just going to use 4 bits. I don't need all of the zeros on the end for a byte, so I'm just going to use 4 bits to represent 6 in decimal, which in binary is 0, 1, 1, 0. Okay, so that's 6 in binary. Now if we just jump, imagine that we've counted up and we've just jumped to 12 in decimal, the binary equivalent of 12 is 1, 1, 0, 0. Can you see a pattern between this binary number and this binary number as a result of doubling in decimal? And the pattern actually is that these two numbers are the same if you take this number and shift it over to the left hand side, so that each digit occupies the next space along on the left hand side. So that occupies that space, that's moved up to the left, and that's moved up to the left, and then we just add this 0, we just add on the end out of convenience, I was going to say, but that's probably the wrong expression. So if we shift a binary number to the left hand side, if we shift all of the digits into the slot on the left hand side, it is the equivalent of doubling in decimal. And likewise, guys, if we wanted to we can do it the other way around as well. If we wanted to halve in decimal, then we shift the digits over to the left hand side. So if I just go backwards and we look at 3 in base 10, okay, obviously 6 halved is 3. So if I shift my binary numbers over to the right hand side to get a smaller representation in binary, I should get the equivalent of 3. So let's do that then. Let's shift our numbers over to the right hand side. So that shifted over goes there. Let's use the pen actually. That shifted over, okay, gives me the 1. The 0 drops off the end. That shifted over, okay, gives me the 1 there. And then what I've got left is 0, 0 on the left hand side, okay. So can you see that the pattern here is each time we want to double 3, 6, 12, we shift the digits over to the left hand side. If we want to go back the other way and go from 12 to 6 to 3 and halve, we just shift the binary digits one place to the right. So likewise, guys, if I wanted to calculate 24 in base 10, I'm going to need an extra space to do that. Okay, so it's basically going to be, shift these over to the side, it's going to be 1, 1, 0, 0, 0. Okay, it's going to be 24 in the base 10 because I shifted them all over. And just to make sure I don't cause any confusion, if I just put another column of zeros at the top, guys, here, okay, you can see now that we've got 1, 1, 0, 0, 0 in base 2 is the equivalent of 24 in base 10. Okay, so this is the pattern then that begins to emerge. Okay, we're shifting all of these to the right and to the left hand side. So we can use that essentially, and of course it will get used because you will quite often get an exam in a question in an exam or assessment, which is simply asking you to right and left shift. So let's look at another example. We'll look at a slightly larger number. So let's take the binary equivalent of 10. So let's imagine if in an exam or assessment, guys, it says if 10, okay, in base 10 is represented by 0, 0, 0, 0, 1, 0, 1, 0, okay, what is 20? okay, in binary. And all we do, guys, okay, based on what we were saying earlier, is we take 1010 and we shift it all over to the left hand side. Okay, so we will have 0001, okay, because we're shifting this over to the next column. Okay, and then we will have 010, and then we need to put a 0 on the end, okay, to cater to the fact that we shifted everything over to the left hand side, guys. Okay, so that goes there, okay, that goes there, that goes there, that goes there, and then we just put a 0 on the end, okay, to make sure that we've got 8. 1 2 3 4 5 6 7 8. And again, guys, if you check using a converter on the internet, you will find that 20 in denary is the equivalent of that number in binary. Okay, so of course, guys, remember that if in an exam this is your working out, so you would of course want to put down your final answer. 20 in base 10 equals 0001010, okay, in base 2. So that would be your final answer. Okay, so in this part of the video, guys, we're going to be looking at binary addition. And binary addition sort of takes you back to primary school a little bit, because in the good old days it used to be hundreds, tens and units, and then you guys figured out that you needed to carry one over into the next column because there wasn't space to put 2 digits in one column, and you used to have to do a carryover. And we do something very similar in binary, but we do need to practice a little bit because it's a different number system. All right, so this is what we're going to do. And to prove the point that addition works, we're simply going to count up in binary by adding 1 each time. All right, and then we can we know what the first few numbers are in binary, so we can simply prove the point by comparing. So let's do a little column here. Let's count up 0 1 2 3 4 5 and 6. Okay, so this is going to be decimal. All right, and then our binary equivalent. Okay, so we're going to start off, guys. I'm not going to put all of the zeros in to represent a byte, okay, because it'll be too long. So we'll do 0000. Okay, the next number, guys, the binary representation of 1 is 3 zeros and a 1. Then we have 0010, 0011, 0100, 0101. Okay, and then 0110. Okay, so that's some simple counting, and we can prove that if we add 1 to these each time, we should get the same as we've already written down in our column. Okay, so let's show that this works then. So 0000 plus 1. Okay, so 1 and 0 is 1. Okay, and then 0 and 0, 0 plus 0, 0 plus 0, guys, it's just zeros. Okay. So 0 and a 1 is going to give us 0001. Okay, no surprises there. So let's add 1 to this number here to give us 0010. Okay, so let's take again, we'll just put in here plus 1. Okay, now in binary, 1 plus 1 is 10. Okay, but we haven't got space to put 10 in one column, so we carry across the 1. Right, let's put it up there. Okay, 1 and 1 is 10, so put the 0 there. Okay, and then 0 plus the 1 I've carried over gives me 1, and then these are all zeros, guys, so I get 0010, which is what we get there. Let's add another 1 then. Okay, let's put it in the right place, that would help. Okay, 1 and 0 is 1, 1 and 0 is 0. Sorry, 1 and 0 is 1, 0 and 0 is 0, 0, 0 is 0. Okay, so 3, guys. Right, we've got 0, 1, 0, 0, 1, 1, which is correct. Okay, let's add another 1. Okay, so we should get 4. Okay, which is 0, 1, 0, 0. So let's add 1 to this. Okay, 1 and 1 is 1, 0, but we need to carry over. So we carry over the 1 to there, and that becomes 0. Same again, 1 and 1 is 1, 0, but we need to do a carryover. Okay, so that becomes 0, and we carry 1 over again. Okay, 1 and 0 is 1. Okay, so we have 0, 1, 0, 0. Okay, which is exactly what we have there. Okay, and so it continues, guys. So the most important thing to realize is that whenever you have to add a 1 and a 1, that's going to be a carryover. So 1 and 1, you drop down the 0 and carry 1 over. Okay, and then you carry on with the same technique. So it's exactly what you used to do years ago in primary school, except that you have to remember you're working with a different number system, so the rule is slightly different, okay, but it's the same technique. Okay, so now that we've got that sorted, let's do a bit of binary addition with a slightly larger number. So let's look at, in fact, we're going to, well, let's add up a couple of numbers which we saw a little bit earlier on, guys. So let's add up 6 in decimal and 12 in decimal. Of course gives us 18, but we want to do that in binary, guys. Okay, so let's say that we're given these two numbers. All right, so 6 in base 10 is equivalent of 1 2 3 4 5 1 1 0. Okay, so 6 in base 10 is 0 0 0 0 0 1 1 0. Okay, and then 12. All right, should we do a left shift for the 12? Okay, I don't even need to look that up then. So if we shift all of these over, okay, I'm going to get 0 0 0 0 1 1 0 0. Okay, in base 2. Okay, guys, do make sure when you do the addition, just like you do when you do decimal addition, is exactly what I've managed not to do here, which is to make sure that you have got your numbers lined up in the right columns, guys. Otherwise it's error prone. So we basically need to add these two together using the same technique we saw earlier with the carryover. We should, okay, get the binary equivalent of 18 in base 10, and we'll check that a little bit later on. Okay, so let's go through this, okay, step by step. 0 and 0, okay, gives us 0. 1 and 0 gives us 1. Okay, 1 and 1 gives us 0 carryover. Okay, 1 and 1 gives us 0 carryover. Okay, 1 and 0 gives us 1. Okay, 1 2 3 4 5 6 7 8. So 18 in base 2, okay, is 0 0 0 1 0 0 1 0. Okay, now don't forget that this is our working, so our final answer would be 18 in base 10 is the equivalent of 1 2 3 1 0 0 1 0 in base 2, guys. And again, you can check this if you want to using a converter on the internet. Shall we, mainly because I've just thought of it, shall we check this by converting, using our technique for converting a binary number into decimal? Should we check that this number actually is 18? Okay, let's do that then, by virtue of a bit of revision. Okay, let's do a conversion. So we're going to start off here, guys. I'll just write this down before I lose it. Okay, we want to convert 0 0 0 1 0 0 1 0 in base 2, and we want to convert that into decimal. All right, so let's use the technique, guys, that you have looked at previously. So of course, whenever we need to do a conversion involving binary, it's helpful to write down our magic numbers. Okay, so 1 2 8 64 32 16 8 4 2 and 1. And of course, if you remember, guys, you take your binary numbers and you drop them down underneath. So we have 0 0 1 0 0 1 0, and what we look for is where we have got a 1 sitting out underneath our magic numbers, and we drop down the magic number and add them together. So we have 16 plus 2, which of course gives us 18 in base 10. Don't forget that this is your working out, so we would say 0 0 0 1 0 0 1 0 in base 2 is equivalent to 18 in base 10. All right, so we've just proved that we got our previous answer correct, that indeed 0 0 0 1 0 0 1 0 is indeed 18 in base 10 ordinary. Okay, so I just thought we would do that as a bit of practice and a bit of an aside. Okay, let's do another addition then. Let's add up, let's do 10 and 20, and we'll do a shift, okay, to get us the number 20. So let's start off with 10. Okay, so 10 in base 10 is equivalent of 1 2 3 4 1 0 1 0. Okay, 20 in base 10, guys. Let's do a left shift to give us that. So we have 1 2 3 1 0 1 0 0 in base 2, guys. We've shifted our numbers over to the left hand side to go from 10 to 20, or the equivalent. When we add these two together, we should of course get 30. All right, so that's what we're after. So let's follow this through then step by step, guys. So 0 and 0 gives us 0. 1 and 0 gives us 1. 0 and 1 gives us 1. Okay, 1 and 0 gives us 1. 1 and 0 gives us 1. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so don't forget then that this is our working out. So we would want to say 30 base 10 is the equivalent of 1, 2, 3, 1, 2, 3, 4, and then 0 at the end. Okay, so whilst you're doing your practice, guys, you can use a converter to double check, and you'll find that 30 base 10 is indeed 0, 0, 0, 1, 2, 1, 1, 1, 1, 0, guys. Okay, so you are not going to be asked in an assessment or an exam to do anything more complicated than what you've seen in the demos here, guys. Okay, and it's just a question of, like I said before, being very, very methodical and just doing it step by step. Okay, 1 plus 1 equals 1, 0, but you have to carry the 1 across, so it becomes 0. Carry the 1 over, guys. Okay, and then just make sure that you've got your working out nice and neat, so you don't make any errors in the process. So guys, in this part of the video, we are going to be converting hex to binary and binary to hex. And I know that students can find this a little bit intimidating, but in actual fact, again, if you are methodical and you follow the techniques that you have learnt, you will find actually that the process for doing this, the steps for doing this, are using the same types of techniques that we used for binary and decimal and binary as well. So we're combining them together, and if you think about it, it all makes perfect sense, I promise. So to start with, guys, let's remember that with the hex number system, we have to use letters to cater to the fact that we need to go beyond 9, but of course in decimal we don't have any characters to represent beyond 9 because we go back to 0 again, so we have to cater for that by using alpha characters. So if I just pop down on the right hand side, just a reminder that in the hex number system we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now of course in decimal we go back to beginning it again, and then we would make a note of the fact that we have completed one complete cycle of 0 to 9. But hex doesn't work like that because it's base 16. So we need to have some extra characters. We use alpha characters, uppercase, and of course it goes to A, B. Okay, so this is the equivalent in decimal of 10, 11, 12, 13, 14, and 15. And then of course, just like in decimal going from 9 back to 0, in hex we go from F, which is the decimal equivalent of 15, back to 0. Okay, so I will try and hopefully I've got enough space. If I leave this up on the right hand side, guys, I can leave that there for reference. So just put a little line down there, and I'll just put, okay, the decimal equivalent, so 10, 11, 12, 13, 14, and 15. Okay, so these numbers in pink are the decimal equivalent of the characters that we're representing hex. Okay, so hex, okay, which is base 16. Right, there's one very, very important thing that you always need to remember when you are working with hex, and is that each hex character, all right, whether it's a letter or a number, is representing 4 bits. Right, this is really important to remember, 4 bits per character that you're given in an assessment or an exam, and you'll see why this is important a little bit later on. So let's start off with 1, 3. Remember, we can't say 13, okay, because 13 is the terminology we use for denary or base 10. We have to say 1, 3, right, because it's not 13 in hex, it's 1, 3. And we want to find out what that is in base 2 or binary. So what we do is we take the 1 and the 3, okay, and we can work with 1 and 3, okay, because these are numbers, all right, so we haven't got to the added complexity of dealing with the letters yet. So this is a nice simple one. All right, so 1, 3 in base 16 or hex. The first thing that we do, all right, is we need to split those out, okay, so we take each of our characters in turn in our hex expression, and remembering that each one of these will represent 4 bits. All right, now to convert it to binary, of course, we're going to need our magic number line, but if we're only dealing with 4 bits, we only need part of our magic number line that caters for the first 4 bits. And if you remember, that's 8, 4, 2 and 1. Okay, so we don't need to write the 128, 64, 32, 16 because we're never going to use them because it's just 4 bits. So we just start off by writing down the equivalent or the useful part of our magic number line for binary, which is 8, 4, 2 and 1. And of course I could put 128, 64, 32, 16, but I don't need to because I'm never going to use them. Okay, so 8, 4, 2, 1. And then just like we did before, we want to find a way of representing the number 1 using our magic number line. Now with hex type questions, guys, it's unlikely to be the case that you're not going to be able to make up one of these numbers, okay, by seeing straight away how you can assemble that from 8, 4 and 2 and 1. Okay, so 1, to create 1 out of our choice of numbers is obviously we just use the 1. Okay, we don't need anything else, so we're going to need a 1, right, and we could just put zeros for the others. Okay, so this is essentially what we did when we were converting, okay, a decimal number to binary. All right, this is the same technique, we're just incorporating it into the overall way that we work with hex. Okay, so 8, 4, 2 and 1. So in other words, the number 1 is the equivalent of 0, 0, 0, 1 in base 2, guys. Okay, and we do the same thing for the 3. All right, so we take the character in the other part of the number, write down our magic number line that was going to be useful for us, 8, 4, 2, 1. We want to make up the number 3, okay, from any combinations of 8, 4, 2, 1, and we can do that with 2 plus 1. Okay, so let's make a note of the numbers in our magic number line, okay, which give us, when added together, give us 3. Okay, so we can put zeros for the numbers we don't want. So all we simply do now is pop them back to back, okay, to give us our binary equivalent. So don't forget this as you're working out. So 1, 3, almost said 13 then, didn't I? But you didn't notice. 1, 3 in base 16 is the equivalent of 0, 0, 0, 1. Okay, and then let's put this back to back, 0, 0, 1, 1 in base 2. And again, guys, you can check this out. Okay, you can go onto a number system converter and check that 13 in hex is the equivalent, okay, of 0, 0, 0, 1, 0, 0, 1, 1 to the base 2. So let's look at a slightly more complicated version, because we're not always going to get something nice where we've got hex that doesn't use any of our alpha characters. So let's use one that does use some of our alpha character representation, okay, in base 16. So let's rub this out, and let's say that the one that we've been given to do is, let's do A7. Okay, so on this occasion in base 16 we're using one of our alpha characters to represent a number further up the number line. Okay, so A7, and we want to know what that is in base 2 or binary. So we do exactly the same thing again. All right, we write down A7, and remembering that each one of our 2 characters in our hex representation is going to be represented by 4 bits. And we do exactly the same thing as we did before. The only thing is we want to change A into the decimal equivalent, because we can't work with letters, we've got to be working with numbers. So I want to change A into its decimal equivalent, which is 10. So I'm going to put 10 down there instead of A, and I'm just going to leave the 7 as is, because I can work with the 7, that's fine. And then what we do is exactly the same as we did before. All right, so to convert into binary, we're going to want those 4 useful numbers on our magic number line, which is 8, 4, 2 and 1. Same over here, 8, 4, 2 and 1. And we want to be able to construct the number 10 out of the numbers on our magic number line, just as we've done before. And we can make 10 out of 8 plus 2. So 8 and 2, and then we put a 0 where we don't need to use those numbers. Okay, so that gives us 1010, and then we do exactly the same on the other side. How do I make 7? I can make 7 with 4 plus 2 plus 1. So I don't need the 8, 4 plus 2 plus 1. Okay, that will give me 7. All right, and then I just put them back to back. So my final answer is A7 in base 16, or hex, is the equivalent of 1010, and then put that alongside 0, 1, 1, 1, okay, in base 2. So A7 base 16 or hexadecimal is the equivalent of 10100,111 in base 2. And again, guys, you can check that out just by checking on a converter to make sure that you have actually got the answer correct if you wish to do so while you're practicing. Practice makes perfect with these guys, okay? The more you can practice, the better. Okay, so we want to be able to convert from binary up to hex. So not surprisingly, we're essentially going to be doing this process in reverse, which is always the case. We're basically doing one process in reverse to go in the other direction. So let's take the numbers that we've calculated from our two examples and let's work back to make sure we get the same examples. Okay, so let's say that we want to convert 0, 0, 0, 1, 0, 0, 1, 1. Okay, so if you remember, this is what we used in the first example. This is 1, 3 in base 16 or hexadecimal. All right, so how do we actually get to that? Okay, so what is it in base 16? What we do is we take our byte representation, so 1, 2, 3, 1, 1, 2, 1, 1. Okay, so we must make sure that we're working with a full byte, all right, which will happen in an assessment or exam, guys. That'll be fine. Okay, and what we do is we split our byte into two separate sets of bits, okay, into a nibble, left hand side and right hand side. So we've got 4 bits. And if you remember, with hex, we're always working with chunks of 4 bits. That's the first thing we need to do, okay, is to separate our 8 bits, our byte, into 2 nibbles or 2 4-bit chunks, okay. And then what we want to do is we want to work with each of these in turn. Okay, so how do we do that? Well, essentially what we want to do is it's like converting our binary into decimal. How do we do that then? Well, we simply take our magic number line, just like we did before, 8, 4, 2, 1. Okay, and then same on this side, 8, 4, 2, 1. We want to see, okay, where we have a 1 that corresponds to a number on our magic number line. So here, guys, we have a 1. Okay, so you can make a note of the number 1 on that side. And here you can see that we have a 2 plus 1, okay, because we've got a 1 underneath each of these numbers in our magic number line. So just like we're converting to decimal, okay, we take each of these and add them together, and of course we get 3. All right, and then once again, we simply put them back to back. So we have 1 and 3, okay, in hex or base 16. So don't forget this is your working then. So we would say 0, 0, 0, 1, 0, 0, 1, 1 to the base 2 is the equivalent of 1, 3 in base 16. And we know that because this is a number that we did the first example in when we worked in the other direction. So let's see if we can do our previous example in reverse when we need to get from a binary number, okay, to A7. Do you remember that one? So let's do the one that we started off with, A7. So the answer that we actually got was we had 1010 and then we had 0111. Okay, and what we're expecting, we want to convert that to hex, so we expect, of course, guys, for this to be A7. All right, let's show that that's the case, okay, in base 16 or hexadecimal. So let's do exactly the same thing there. We write down our number 1010 0111, and then we split it so that we have 4 bits on each side, okay, and then we write our magic number line on top, 8421, 8421, and then just like when we converted to decimal, we're looking for, okay, the numbers that correspond with the ones in our binary number, okay, and then we add them up. So here we've got 8 plus 2, so that gives us 10. And on this side, we've got 4, 5, 6, 7. Okay, because we've got 4 plus 2 plus 1, 4, 5, 6, 7. Okay, that gives us 7. Now, normally, of course, we would put the 10 and the 7 side by side, but we can't because 10 doesn't exist in hex. We've got to translate 10 into the alpha character equivalent. So if you look over here, just like we did before, okay, 10 is represented by A in hex. So we could, if you wanted to, you could write this. Okay, and then you could just translate that into A7, okay, in 16. So don't forget this is your working. So I know you're fed up with me saying that. Okay, but 10100111 base 2 is the equivalent of A7 in base 16. So go away and have lots of practice. Guys, invent some numbers, right, and then have a go at converting binary to decimal, decimal to binary, hex to binary, binary to hex. Okay, and then check them on a converter, and likewise practice your right shifts and your left shifts. Left shift if you're going up and you're doubling, right shift if you're halving in decimal, and also practice a little bit of addition. And don't forget, of course, you can check with number system converters on the internet to make sure you've got the right answers. Practice, guys, okay, in preparation for any assessments or exams you might have. Hope these series of videos were useful. I will see you in a future video, guys.